In the previous two videos, we derived the error probability for binary signaling, and we did it for two different cases. One was the binary unipolar signaling, and then we also did the same process for binary polar signaling, and we got the error probabilities for both the cases. So in the case of binary unipolar signaling, we got the error probability, the average probability of error, PE, as the Q function of A by 2 sigma, where A is the voltage level separation between the voltage level used to represent a 0 and a 1. So in the case of unipolar, 0 is represented as 0 volt. So 0 is represented as 0 volt, and a bit 1 is represented as a positive voltage level, which we denote as A volt. So it is unipolar with a voltage level separation of A volt, and we got the error probability as Q function Q of A by 2 sigma. Similarly, we did an analysis for binary polar signaling. And we again got the error probability PE as Q function of A by 2 sigma. Again, for the polar signaling, we represent a 0 as a negative voltage, which we denoted as minus A by 2, and a bit 1 as a positive voltage, which we used as plus A by 2. Again, the choice of these voltage levels has been such that the voltage separation between a 0 and a 1 is A volt. From minus A by 2 to plus A by 2, the distance is A volt. So because we want to compare unipolar with polar signaling, we chose the voltage level separation to be the same. So in this case, it's unipolar with the voltage separation of A volt. Here it is polar. It has both negative and positive voltage, but the distance between the two voltage levels is still A volt. And what we noticed was that in terms of the expression for the error probabilities, the unipolar signaling and polar signaling had the same expression for the average error probability. But we later on, towards the end of the previous video, we looked at what this A by 2 sigma represents, which is the argument of the Q function, right? And we found that A by 2 sigma represents the signal to noise ratio in both the cases, and from that we determined that polar signaling offers the signal to noise ratio advantage by a factor of root 2. So this is what we evaluated. We evaluated A by 2 sigma, and we got that as A by 2 sigma is equal to, for the unipolar and the polar case, we got it as 1 by root 2 and into the square root of the signal to noise ratio, which is SR by NR, and that is for the unipolar case. And then in the polar case, we got it simply as the square root of signal to noise ratio, which is SR by NR, and that is for the polar signaling case, the binary polar case. So from this expression, what we interpreted was that in terms of the expression, it looks like the error probability is the same for both unipolar and polar signaling, but in reality, this A by 2 sigma is representing two different parameters in each of the cases. In unipolar, this A by 2 sigma is denoting the square root of signal to noise ratio divided by root 2. And in the case of polar signaling, the A by 2 sigma is representing the square root of signal to noise ratio. And because we have a root 2 factor, which is root 2 is greater than 1, and that's in the denominator here, that means this threshold is actually less in the unipolar case. So the error probability, if we plot the Gaussian PDF, which is centered on 0, so that's centered on 0, so the error probability is given by this, and this is the Q of A by 2 sigma. But the difference is that in the case of unipolar, this A by 2 sigma, this threshold is smaller, so it is somewhere here. So that means the error probability is actually bigger in the case of unipolar signal because it is covering a much bigger area, right? It is smaller by a factor of √2, so therefore it is having a bigger area to the right of it. That means the error probability is more in the case of unipolar signaling as compared to polar signaling. So therefore polar signaling is better by a factor of √2. Of √2 compared to unipolar signaling. Okay, so clearly we have to choose polar signaling because it has an advantage in terms of the signal to noise ratio by a factor of √2. So therefore, when we go for the from binary signaling to M-ary signaling, we will choose polar signaling because polar signaling is indeed better. So in today's video, we are going to compute the error probability for M-ary signaling, and we will start with m equal to 4. Binary means m equal to 2. We have only two symbols, a 0 or a 1. But in M-ary, we can have more than two signals. It could be 4, 8, 16, 32, and so on. We will first do it for 4, and then using the ideas that we developed for M-ary signaling with m equal to 4, we will extend the results to any arbitrary value of m. Of course, m should be a power of 2. It can take values of 2, 4, 8, 16, and so on. So we will first do it for m equal to 4. So that is 4-ary signaling, where we will have 4 symbols or 4 voltage levels, and we will use polar signaling because polar is better than unipolar. And once we have derived the expression for error probability for 4-ary signaling, we will then derive the general expression for M-ary signaling's error probability for any value of m. Okay, so let us start our analysis with m equal to 4. In m equal to 4, we are going to combine 2 bits at a time so that it gives us 4 possible symbols. So let's do it for M-ary signaling with m equal to 4. So what happens is, if we have a bit stream, let's say 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, and so on, right? We have a stream of bits. So when m is equal to 4, we are going to combine 2 bits at a time and represent them as symbols. So when you combine 2 bits at a time, we can have 4 possible combinations. So we can have either the bit combination as 0, 0, or it could be 0, 1, or it could be 1, 0, or 1, 1. So there are 4 possible combinations that these 2-bit pairs can take. Now, we are going to call them as symbols. So 0, 0, we'll call it as symbol 0, symbol M0 or message M0. 0, 1, we'll call it as symbol or message M1. 1, 0 is our third message, which we'll call as M2. And 1, 1, we'll call it as M3. So we have 4 symbols, okay? Each symbol is having a length of 2 bits. So M0 is a symbol with a length of 2 bits. M1 is a symbol with a length of 2 bits, and so on. So we have 4 possible symbols. That's why we call it as 4-ary signaling. M-ary with m equal to 4. So we can write that in bracket as 4-ary signaling. And since we have already seen that the polar signaling is better than unipolar, we are going to represent these four symbols using four different voltage levels, and we will use the polar voltage level. So that means we'll use two of these symbols, or we'll represent two of these symbols with a negative voltage level and two with a positive voltage level. So we are going to represent M0 with a voltage level, let's say minus 3A by 2. M1 will represent it as minus A by 2, that's volt. And M2 will represent it as plus A by 2 volt, and M3 as plus 3A by 2 volt. So basically what we are doing is we have represented them with some amplitude levels, and the separation between any two amplitude levels is A. So from minus A by 2 to minus 3A by 2 it's A. From minus A by 2 to plus A by 2 is also A, and from A by 2 to 3A by 2 the distance is still A. So we have kept the voltage level separation still as A volt, just as we did in the binary cases for both unipolar and polar. Again, we are doing it so that we are consistent with our representation. Okay, so we have four different voltage levels, and because it's polar signaling, we have two of them with the negative voltage level and two with the positive voltage level. So the transmitted sequence is going to look something like this. So I'm just going to draw the voltage levels for a couple of symbols. For example, the first bit sequence we have here is 0 1. So 0 1 is M1, and that is minus A by 2. So we have four voltage levels: minus A by 2, plus A by 2, minus 3A by 2, and plus 3A by 2. So in this bit sequence that we have, the first symbol we have is 0 1, which is M1, and it's minus A by 2 volt. So it will be at minus A by 2. It will be a voltage level minus A by 2, and that's minus 3A by 2, and that is plus A by 2, and that is plus 3A by 2. Then the next bit combination, or next symbol that we have, is 0 0, and 0 0 is M0, which is minus 3A by 2. So we'll have it as minus 3A by 2. So that's our next pulse. And then the next bit sequence we have here is 0 1 again. So 0 1 is again M1. So and M1 is again minus A by 2. So we'll have it as minus A by 2. And then we have the fourth symbol as 1 0. 1 0 is M2, which is plus A by 2. So plus A by 2, so that will be plus A by 2 volts. And the fifth symbol is 1 1. So 1 1, so 1 2 3 4, so fifth is 1 1, and 1 1 is M3, which is plus 3A by 2. So that will be at plus 3A by 2 volt. Okay, so that way we have our symbols represented by different voltage levels. So that is M0, which is 0 0. Then we have minus 3A by 2. No, M0 is, the first one is minus A by 2, which is 0 1. The second one is M0, which is 0 0. And then we have again 0 1, 1 0, 1 1, right? So each voltage level is now representing two bits of information. So in M-ary signaling, we are trying to represent more bits within one symbol duration, so that way we can keep the width of the pulse larger, but we have more bits within that time duration. So rather than one symbol representing one bit in the binary case, now we have one symbol representing two bits of information. That means if we transmit one pulse, that we are transmitting 2 bits. So in the same time as one pulse, there are 2 bits of information that are being transmitted. Okay, so these are the voltage levels that are going to be transmitted depending on the symbols that we get in our bit sequence. So we call this as our input signals which is denoted as X. So the transmitted signal X is equal to, it can be one of these four combinations. It can be 0 0 or 0 1 or 1 0 or 1 1, and according to that it will be having one of these four voltage levels. So X is one of these four voltage levels. Now the received signal Y is going to be the transmitted signal plus noise, because the channel adds the received signal Y is equal to the transmitted signal X plus noise. And because the transmitted signal can take one of these four possible values, the received signal can be one of these four possibilities. It can be minus 3A by 2 plus noise if we are transmitting M0, or it can be minus A by 2 plus noise if we are transmitting M1, or it can be plus A by 2 plus noise when M2 is transmitted, or it will be plus 3A by 2 plus noise when M3 is transmitted. So we have four possibilities for the received signal Y, depending on what was transmitted. And the noise here is zero mean Gaussian noise like before. So noise N is zero mean Gaussian noise. That means the noise is going to have a PDF which is centered on 0, and it has a Gaussian distribution. So that's the probability density function of noise, and that's noise, and it is having a mean value of 0. That means it is centered on 0. So that's the mean 0. Now to this noise, some constant is going to get added. So whenever we transmit M0, the received signal Y is going to have a probability density function, which is a shifted version of this, and it will be shifted by minus 3A by 2. That means it will be shifted to the left and be centered on minus 3A by 2. Similarly, when we transmit M1, then that means we are transmitting minus A by 2 plus noise. So the received signal would be minus A by 2 plus noise. Noise is zero mean, and to that zero mean, when we add minus A by 2, this will get shifted and be centered on minus A by 2. Similarly, when M2 is transmitted, the PDF of the received signal would be the noise PDF centered on plus A by 2. It will be shifted to the right by A by 2 because we are adding plus A by 2 here. And when M3 is transmitted, then the received signal Y will have a PDF centered on plus 3A by 2. So these will be the conditional PDFs of the received signal Y depending on what was transmitted. So the conditional PDFs of the received signal Y are shown here, where this blue PDF represents the PDF of the received signal when M0 is transmitted. So it is P of Y on the condition that M0 is transmitted, in which case it will be centered on minus 3A by 2. So because for M0 we are transmitting a voltage level of minus 3A by 2, this noise PDF, which was centered on 0, will get shifted and centered on minus 3A by 2 whenever M0 is transmitted. So the blue PDF is the conditional PDF P of Y on the condition that M0 is transmitted. Similarly, when M1 is transmitted, we'll have this P of Y given M1. So when M0 is transmitted, it is going to be centered on minus 3A by 2, and when M1 is transmitted, it is centered on minus A by 2, and when M2 is transmitted, it is going to be centered on plus A by 2. So this black PDF is the conditional PDF of the received signal Y on the condition that M2 is transmitted, and that will be centered on plus A by 2, because when M2 is transmitted, the transmitted voltage level is plus A by 2, to which the zero mean Gaussian noise gets added. So this will be shifted to and be centered on plus A by 2. And then when M3 is transmitted, the received PDF will be centered on plus 3A by 2. So this green PDF is the conditional PDF of the received signal Y on the condition that M3 is transmitted. So we have our four symbols, M0, M1, M2 and M3, and depending on which of the four symbols is transmitted, the received signal will have a conditional PDF, P of Y given M0 or P of Y given M1 and so on, and they will be centered on their respective voltage levels. So when M0 is transmitted, the received signal will have a mean value of minus 3A by 2. When M1 is transmitted, the received signal has a mean value of minus A by 2, and when M2 is transmitted, the mean value is plus A by 2, and for M3 being transmitted, the mean value is plus 3A by 2. So now we have the conditional PDFs of the four received signals depending on what was transmitted. Now that's M0, M1, M2 or M3. Now once we have done this, the next step is to identify the decision thresholds. Now because we have four PDFs here, there are going to be three thresholds. So we are going to have three different thresholds. The thresholds, like before, will be the intersection points of the conditional PDF. So we have an intersection here. So at the value on the x-axis at which this intersection happens, that would be one of our thresholds. There is a second intersection here, so that is the second threshold, and there's a third intersection here, so that is our third threshold. So we are going to have three different decision thresholds. So I'm going to mark those thresholds now. So the first of the three thresholds is here. The second one is the first one is here. The second decision threshold is here, and the third is at this intersection, which is here. So we have the three decision thresholds, and by the symmetry of the Gaussian PDFs, the intersection of any two adjacent PDFs will occur exactly midway between their centers. So this intersection would be exactly in the middle of minus 3A by 2 and minus A by 2. So that would be exactly at minus A. So the midpoint between minus 3A by 2 and minus A by 2 is minus A. The midpoint between minus A by 2 and plus A by 2, so that's the midpoint, that would be 0. So that's by the symmetric nature of the Gaussian PDF, that the intersection of these two adjacent PDFs will happen exactly midway between their mean values. And similarly, between A by 2 and 3A by 2, the midway point would be plus A. So those are the three decision thresholds. So we have decision thresholds, which are minus A, 0 and plus A. Once we have our decision thresholds, we can now proceed with our decision rule. What would be the decision rule? If the received signal Y is below minus A, if the received signal Y is less than minus A volt, we will decide in favor of M0, because when the received voltage level is less than minus A, that means to the left of minus A, the probability for M0 is largest, because this curve, the blue curve, which is the PDF of the received signal when M0 is transmitted, has the highest area on the left hand side of minus A. So that means M0 has more probability of being transmitted when the received signal Y is below minus A. When the received signal y is between minus A and 0, between minus A and 0, that is to the right of minus A but to the left of 0, this red PDF has the largest area in that interval from minus A to 0. So that means the symbol corresponding to the red PDF will have the highest probability if the received signal is between minus A and 0. So that means M1. So the decision rule would be, if the received signal y is less than minus A, decide M0. If it is between minus A and 0, decide M1. If it is between 0 and A, decide M2. And if the received signal y is greater than A volt, decide in favor of M3. So that would be our decision rule. So the decision rule is going to be, if the received signal y is less than minus A, decide M0. If the received signal y is between minus A and 0, then we will decide in favor of M1, because in that interval the PDF for M1 has the highest area, right? Has the largest area. So between minus A and 0. So when the received signal y is between minus A and 0, decide M1. When it is between 0 and A, then this black PDF has the largest area, so we will decide M2. So when the received signal y is between 0 and A, then we decide M2. And when it is greater than plus A, that means to the right of this threshold A, the area under the green PDF is largest, so that means the probability of M3 is largest in that case. So if when y, that is the received signal y, is greater than A, decide M3. Okay, and occasionally it could be possible, but it would be a rare case, that the received signal y is exactly equal to one of these thresholds. It could be either exactly minus A, or exactly 0, or exactly plus A, in which case we have to choose any one of the symbols which are adjacent randomly. Okay, now if it is exactly minus A, we are going to give it to M1, for example. We can choose whichever we want. So if it is exactly minus A, we will choose M1. So between minus A and 0, and even including minus A. If it is exactly 0, that is this threshold, we can choose either M1 or M2, but I'll give it to, let's say, M2. So let's say M2. So between, if it's exactly 0 also, we'll choose M2. Again, we could have chosen M1 also here. So that is arbitrary, and that is a very rare case anyway. And if it's exactly plus A, then we can choose either M2 or M3, but we will choose M2 again. The reason why we give this equality in favor of the symbols which are in between, because the symbols which are in between have two boundaries. So M1 has a boundary on the left and at the right. So if it goes outside the left boundary or outside the right boundary, it will go to the neighboring symbol. But if you look at the two extreme symbols which are on the outside, they have only one boundary. On the other side, it's open. There is no boundary. It can go as far as it wants. Similarly, for M3, it has a boundary only on the left side. On the right side, it is open for it. But M1 and M2, they have boundaries on both sides, okay, to the left as well as right. So this equality space, we will give it in favor of the symbols which are in the middle. Okay, so in this case I have given this minus A in favor of M1, and 0 and plus A both I have given in favor of M2. Okay, and again you could have chosen either M1 or M2 for 0 as well. that is arbitrary, and that is going to be a very rare case anyway. So we have our decision rule decided here to decide which of the symbols are could have been transmitted based on what is the value of the received signal level. Once we have a decision rule, most of the times we hope that the decision rule will give us the correct symbol that was transmitted, and there should be no errors. But occasionally there could be an error. For example, it could be that we transmitted M0, but the received signal is greater than the threshold -A. So if that situation happens, then this area here represents the error probability when M0 is transmitted. So we will mark this area here, we will highlight here. So this area here represents the, and it goes to infinity by the way, so this area here represents the error probability when M0 is transmitted, which is the transmitted signal is M0, or the transmitted symbol is M0, but the received signal Y is greater than the threshold. And if it is greater than the threshold, the receiver thinks it is M1 or M2 or M3. By the way, this tail goes on, it's never touching 0. It becomes smaller and smaller and smaller, and it becomes 0 at infinity. So it could decide in favor of M1 or M2 or M3. In either case, in all these cases, it's an error. We transmitted M0, but the receiver thinks it is something else other than M0. So that would create and give us an error. So we call this, or we denote this error when M0 is transmitted as PEM0. And we'll write it as PEM0 is the error probability. So let me write the heading here, error probabilities. So when M0 is transmitted, the error probability is the area under this blue PDF to the right of -A. That means from -A to infinity under this PDF P of Y given M0. So PM0, area means integration. So it's the integration from -A to infinity under the PDF when M0 is transmitted, which is P of Y given M0. So that's the error probability when M0 is transmitted. Now we want to represent this error probability in terms of the Q function. To represent this as the Q function, if you recall, the Q function is the area under the Gaussian PDF. Let me draw that a bit properly. So when it is centered on 0, and if we have some threshold here, if we call this as A by 2, then this area here, the area here can be written as Q of A by 2 sigma, right? Provided that this is centered on 0. Now, the PDF that we have here for M0, it is not centered on 0. It is centered on -3A by 2. In order to write this as the Q function, we'll have to shift this to the right and bring it here centered on 0. So from -3A by 2, we have to make it centered on 0. That means we have to shift it to the right by 3A by 2. So because we are only computing the areas, we can shift it and accordingly shift the limits of integration. Okay, when we shift it to the right by 3A by 2, this limit of integration -A will also get shifted to the right by 3A by 2. So we can write that as integral P of Y given M0. We want to shift it to the right, so it's minus, and the amount of shift we want to do is 3A by 2. And the limits of integration will also get shifted by the same amount. By the way, I need to put the variable here, dy, that is dy. So the limit of integration, which is originally -A, that will also get shifted by 3A by 2. So that's that distance here from -A to -A by 2. That's 1A by 2, that's 2A by 2, and 3A by 2. So when we shift it to the right by 3 times A by 2, it will go 1, 2, 3, and it will come to this threshold. So minus a will move to a by 2 when this PDF is moved to the right by 3a by 2 to make it centered on 0. So this will become, the limit of integration will become a by 2, because this minus a has got shifted to the right by 3 times a by 2. So that's 1a by 2, 2a by 2, 3a by 2, it comes to a by 2. So we have a by 2, infinity shifted further to the right remains infinity. So now we'll have this blue PDF something like this, centered on 0, and the cutoff point would be on a by 2. So we'll get it as q of a by 2 sigma. So this error probability is simply the q function of a by 2 sigma. So the probability of error when M0 is transmitted is q function of a by 2 sigma. Now similarly, we can compute the error probability for M1, M2, and M3. We will first do M3 next, because the two symbols which are at the outside, they have only one boundary. Okay, M0 has only one boundary, and similarly M3 also has only one boundary. Then we will do the two symbols which are in between, which have two boundaries. Okay, we will do it one by one. The next error probability that we are going to compute is the error probability when M3 is transmitted. Next, we will compute the error probability when M3 is transmitted, which is the area under the PDF for M3 to the left of the threshold. So the decision rule for M3 is, if the received signal Y is greater than A, then we decide M3. Now, suppose we transmitted M3 and the received signal is greater than A, the receiver will decide as M3, no error. But if we transmit M3 and the received signal Y is less than A, that is to the left of A, then the receiver will decide maybe M2 or M1 or M0, depending on how far it is to the left. And in all the cases, it will make an error, because the transmitted signal symbol would be M3, the received would be M2 or M1 or M0. Either way, it is going to make an error. So the error probability when M3 is transmitted is the area under the conditional PDF corresponding to M3 being transmitted to the left of the threshold for M3, which is to the left of A. So this area here is denoting the error probability when M3 is transmitted. So now we are going to represent this as an equation. So the error probability when M3 is transmitted is the area, means integral, the area under the conditional PDF for M3 to the left of A. That means from minus infinity to A. This entire area to the left of A, which is from minus infinity to A. Minus infinity to A. So that's the error probability when M3 is transmitted. Now again, we want to represent this as the Q function, and to represent that as a Q function, we need to have this PDF centered on 0. Now the PDF for M3 is centered on 3a by 2, that is plus 3a by 2. So we need to shift this entire green PDF to the left by 3a by 2 and bring it centered on 0. So shifting to the left means plus. So that will be integral P of y given M3. Shift to the left means plus. How much shift? The shift is 3a by 2 dy. The limits of integration will also get shifted by the same amount. So minus infinity, when it is shifted to the left, is still minus infinity, and a, which is here, when it gets shifted to the left by 3 times a by 2, it will come to, that's 1a by 2, 2a by 2, 3a by 2, it will come to minus a by 2. So the limit of integration will come from minus infinity to minus a by 2, which is the area here. So from minus infinity to minus a by 2, and by the symmetric nature of the Gaussian PDF, that is equal to a by 2 to infinity. So these areas are same, okay? This area on the left and this area on the right, they are equal. So we can write it as minus infinity to minus a by 2 when the Gaussian PDF is centered on 0, or we can also write it as a by 2 to infinity. So it can be written as this area or this area because they are mirror images, right? So you can write that as integral a by 2 to infinity p of y given M3, that is the conditional PDF when M3 is transmitted, plus 3a by 2 dy. So that would be this area, which is simply equal to the q function of a by 2 sigma, which is q of a by 2 sigma, because it is from a by 2 to infinity when the Gaussian PDF is centered on 0. So that's equal to q of a by 2 sigma. So what we notice is the two symbols which are at the extreme, right, the left extreme and the right extreme, the symbols which are on the outside, they both have error probability given by the expression q of a by 2 sigma. So the leftmost one is having error probability given by the q function of a by 2 sigma, and the rightmost symbol is also having error probability given by q of a by 2 sigma. So we have computed the error probabilities for M0 and M3, which are on the outsides, okay, and they have only one boundary. The other boundary is not present here, it's open for them, okay. And now we will do for M1 and M2, and that is, we'll compute the error probability for M1 and M2. But notice that M1 and M2 have two boundaries. So M1 here has a boundary on the left and also a boundary on the right. Similarly, M2 has a boundary on the left and on the right. So it has two boundaries on either side. So we will now compute the error probability for M1 and M2. The error probability when M1 is transmitted would be the area under the PDF for M1 to the left of the threshold on the left hand side, which is to the left of minus a, plus the area under the PDF for M1 to the right of 0. So suppose we transmit M1, and if the received signal is between minus a and 0, the receiver will decide it as M1, which would be a correct decision. But if M1 is transmitted and the received signal is below minus a or above 0, then the receiver will decide either as M0 or M2 or M3, because this goes on till infinity, right? So in all these cases it will make an error. So the error probability when M1 is transmitted is the area under the red PDF to the right of 0 as well as to the left of minus a. So we have these two components contributing to the error probability for M1. So this area here and this area here together represent the error probability when M1 is transmitted. So it is the sum of these two areas. So we will now write this mathematically. So the error probability PE M1 when M1 is transmitted is equal to the area under the Gaussian PDF for M1 to the left of minus a plus the area to the right of 0. So to the left of minus a, it is from minus infinity to minus a, the area under P of y given M1 dy. So that is this area to the left hand side, this shaded area here, and then to that we add the second area, which is from 0 to infinity. Under this PDF, P of y given M1, P of y on the condition M1 is transmitted, dy. So this is the error probability when M1 is transmitted. It is the sum of these two areas, which is to the left of -a and to the right of 0 under the conditional PDF when M1 is transmitted. And again, we want to write this as the Q function, and like before, for the Q function, we need to have it centered on 0. So, but now it is centered on -a/2. So we'll have to shift this entire thing to the right by a/2 so that it becomes centered on 0. So we will be shifting this to the right by a/2. So that is the same as integral P of y given M1. Shift to the right is minus, and the amount of shift is a/2 dy. The limits of integration will also get shifted to the right by the same amount. So minus infinity shifted left or right remains minus infinity, and minus a, when shifted to the right by a/2, this will come to minus a/2. So minus infinity, so minus a will become minus a/2 plus this second PDF, this second area. Again, we are going to represent this by making the PDF centered on 0. So it will be P of y given M1 shifted to the right, which is minus. The amount of shift is a/2 dy. The limits of integration will also get shifted to the right by the same amount. So 0 shifted to the right by a/2 will come to a/2. So 0 will become a/2, and infinity remains infinity. So this area here, the first term here, is the area under the PDF when it is centered on 0. So minus infinity to minus a/2 when the PDF, when this red PDF is shifted and centered on 0. So now like this, when it is centered on 0, and when we integrate from minus infinity to minus a/2, that means this area here from minus infinity to minus a/2, and that is nothing but the Q function of a/2 sigma. Similarly, the term on the right hand side here, the second term of this expression, is the area under this PDF centered on 0, that is shifted to the right, centered on 0, and the limit of integration is from a/2 to infinity. So this area here from a/2 to infinity. So that's a Q of a/2 sigma, and that is also Q of a/2 sigma by the symmetric nature of the Gaussian PDF. So this first term is nothing but Q of a/2 sigma, and the second term is also Q of a/2 sigma. So the error probability when M1 is transmitted is Q of a/2 sigma plus another Q of a/2 sigma, which is 2 times Q of a/2 sigma. So that will become equal to Q of a/2 sigma plus Q of a/2 sigma, which is 2 times Q of a/2 sigma. So that's the error probability for M1. Similarly, we will compute the error probability also for M2. So when M2 is transmitted, if the received signal Y is between 0 and A, the receiver will decide in favor of M2. That means there is no error. But if M2 is transmitted and the received signal is less than 0 or greater than A, then there will be an error because the receiver will decide it as either M3 or M1 or M0. So the error probability when M2 is transmitted is the area under the PDF for M2 to the right of A or to the left of 0. So these areas here, these represent the error probability when M2 is transmitted. So that's the error probability when M2 is transmitted. It is the sum of these two areas. So like in the case of M1, we can write these areas as an expression which is PE M2, which is the integral under the conditional PDF when M2 is transmitted, and to the left of 0, so that's to the left of 0, which is from minus infinity to 0 plus the area under that same PDF, P of y given M2 dy to the right of A, that means from A to infinity. Again, we want to represent this as the Q function. To represent it as a Q function, we need to make it centered on 0, and to make it centered on 0, this black PDF, it is centered on A by 2, so we have to shift it to the left by A by 2. So that will become integral P of y given M2, shift to the left means plus, by A by 2 dy. The limits of integration will also get shifted to the left. So minus infinity shifted to the left is minus infinity, and 0 when shifted to the left by A by 2, it will come to minus A by 2. So it's minus infinity to minus A by 2 plus, again it is going to be centered on 0 now, P of y given M2 plus A by 2. The limits of integration are from A to infinity. So when A gets shifted to the left by A by 2, it will come to A by 2. So that becomes A by 2. Infinity shifted to the left remains infinity. So again, it's from minus infinity to minus A by 2 and A by 2 to infinity when it is centered on 0. So it is minus infinity to minus A by 2, and that's A by 2 to infinity. So that is a Q function, and that is another Q function. So we'll have it as simply Q of A by 2 sigma. So that's equal to Q of A by 2 sigma plus Q of A by 2 sigma. So that gives us 2 times Q of A by 2 sigma. So we now have the error probabilities for all the 4 symbols. So for the symbols which are on the outside, the extreme outer symbols, the error probability is Q of A by 2 sigma, and all the symbols which are in between with 2 boundaries, the error probability is double because they have 2 boundaries that they cannot cross. Okay, so the error probability for M1 and M2 is 2 times Q of A by 2 sigma. So these are the error probabilities corresponding to each of the symbols. Now we want to find the average error probability because the transmitted symbols would be a combination of M0, M1, M2 and M3. So we are now interested in computing the average error probability of our reception. So average error probability, which we will simply call as PE. It is the probability that we transmit M0 and there is an error in M0, or the probability that we transmit M1 and there is an error in M1, or the probability that we transmit M2 and there is an error in M2, or the probability that we transmit M3 and there is an error in M3. So that will be the general expression for the average error probability. Now, because we have already chosen the thresholds as the intersection points of the PDFs, that means that is based on the assumption that the 4 symbols are equally likely to be transmitted. So for equally likely symbols, the probability of transmitting M0 is equal to the probability of transmitting M1 is equal to the probability of transmitting M2, which is equal to the probability of transmitting M3. Because we have 4 symbols and all of them are equally likely, that means each of them has a probability of 1 by 4. So the 4 symbols have equal chance of being transmitted, and with each one having a probability of 0.25 or 1/4 or 25%. So we can substitute that as well as the error probabilities for each of the symbols. So the average error probability is 1 by 4 times the error probability when M0 is transmitted, which is Q of A by 2 sigma, plus 1 by 4. When M1 is transmitted, it is 2 times Q of A by 2 sigma. When M2 is transmitted, that's PM2 is 1 by 4 into 2 times Q of A by 2 sigma, because we computed that the symbols which are in between, they have error probability which is 2Q. Okay, and the fourth one is PM3 is 1 by 4, and the outer one is having Q of A by 2 sigma. So now we have the expression for the average error probability, which we just need to simplify now. So we can take the 1 by 4 as a common factor, and that will give us Q of A by 2 sigma plus 2Q of A by 2 sigma plus 2 times Q of A by 2 sigma plus Q of A by 2 sigma, which is equal to 1 by 4 times, that's Q plus 2Q is 3Q, 4, 5Q plus Q is 6 times Q of A by 2 sigma, 6 times Q of A by 2 sigma. So that gives us 3 by 2 times Q of A by 2 sigma. 3 by 2 is 1.5, right? So the average error probability for M-ary signaling with M equal to 4. So we are doing it here this is our calculation for M equal to 4, right? The average error probability for M equal to 4 is 3 by 2 times Q of A by 2 sigma. So that's our final answer. So we are going to use this idea to compute the general expression for any value of M. The idea is that the symbols which are on the outer sides, okay, they are going to have an error probability of only 1Q, and the symbols which are in between, they will have error probability 2Q, because they have 2 boundaries. So if we do for M equal to 8, we will have 2 more to the right and 2 more to the left. Out of them, the last 2, the extreme left and the extreme right, will have an error probability of Q. The remaining 6 in the middle will have an error probability of 2 times Q of A by 2 sigma. And using this idea, we will get the general expression for the error probability for any value of M. Okay, but today we have just derived the expression for the average error probability for M-ary signaling with M equal to 4, and that is equal to 3 by 2 times Q of A by 2 sigma, which is the Q function of A by 2 sigma. Okay, we'll continue with the general expression or deriving the proof for the general expression in the next lecture.